Okay, I don't know what's going on, but my network is really bad right now. Um, I'm just trying to see if something has happened. Anyways, today has been a hectic day. Um, I just I saw this question not long ago. You can see the time is 19:55. So it's been about 5 minutes since I solved this question. I'll explain this and also go through some other topics as well. Oh, okay. This is locked. Sorry, guys. Hello, Ransom. And how are you doing? Okay, so my network is really bad. I probably get the um. I can't really see where my how far I've gone. Streaming because it usually shows on the yeah. Okay, the network is becoming better now. I think. Um. Anyways, we are 48 minutes away from closing time, so let's get started. I've been studying trees for the past 2 days, right? And there has been some application of trees in my past two videos. So if you are new to trees, you can go and watch those videos and also learn from them. Otherwise, if you don't have time to watch the videos there, I have some link in the description. Those are the lectures or those are the articles I read to learn about trees, so you can have access to those as well. Anyways, welcome back. Um, it's been 2 days since I started studying trees, and I just solved this question not too long ago. I think it will be 5 minutes now since I solved this question, right? If you can look this, okay, 30 minutes ago. Sorry. So I will explain this question and how I solved it. It might not look like a big deal, but since I'm still new to trees, this is pretty much a fascinating achievement, right? So let's take a look. The It was supposed to be 1 hour, right? But I think because I was trying to solve my network issues, I lost about maybe 8 minutes. Yeah. All right. So let me close the screen here and bring back my code editor. So right. Okay. So let's get started. Before we start, I would like to revise a few things or revisit some things we learned previously, so that we have that strong memory in head, right? So I'll erase this part. This is my playground file, and I'll come back to this. Let me bring this back. So here is some things I wrote. I'll erase everything so that we start from scratch. All right, so we have a plain canvas now, and like I said, we are on trees, right? So I'm studying trees at this point. I'm studying trees, and trees are basically a data structure that is similar to um, linked lists and arrays in a sense, but more closely to linked lists than arrays. The reason why I mentioned arrays is because it's just storage of a certain data in a particular data structure. So, but the idea with trees is that we store items or nodes. In this case, we store nodes in a branched shape. Let me put it that way, in a branched shape. And the reason why it is closely related to linked lists is because trees and linked lists have something in common, and it's basically called a node, right? So the way we have nodes in a linked list, let me put it like this: node in a linked list. We also have nodes in trees, but there is a difference. There's just a subtle difference between the nodes, or the shape of the node, in a linked list compared to the one in a tree. So in a linked list, our node would look like this. Our node will have two properties. Our node will have a value, right? I'll put a value here. Our node will have a value and the next pointer, right? Now this next will be set to null initially, and this value here will be the value we pass to our node when we instantiate the node class. The next thing we have, and in the case of, sorry, this is linked list. I'll put linked list here. Linked list. Meanwhile, in the case of trees, right, we have nodes that are structured this way. So this is the structure of a node in a tree. So in a tree, we have value, obviously. We'll have a right child, we'll call this right, and we'll have a left child. Now the right and left child are basically, they are also pointers, but like they are also a position at which we can insert, or we can begin to construct a subtree. So let me show you, demonstrate what I mean by that. So let's say, so in a tree we have something called the root, or the root node. The root is basically the beginning of the tree, the main node in a tree, right? So we have it like this. So I'll write, so this is root R here. Now this root is a node in a tree, right? The first node in the tree, and it will have other properties as well. So the value here is R. I represent the value by R. It will have a right child, so we'll represent the right child, or the direction in which the right child will be by sorry, this is the left child, so by this line, and the right child will be on the right hand side. So now when we begin to insert nodes in this tree, we'll either insert them on the right or the left. But there is also one thing we need to note, or take note of, before we insert a node in a tree, is the value of that node compared to all existing node, and basically the root node to begin with. And then we'll decide whether that node that we want to insert in the tree is going to be on the right side or the left side. Now let me change this R here to an actual value. I'll call this a 10, right? And I'll represent the left and right child like this. So this is the left and right child. So let's say I want to insert this value here, 4, into our tree. Well, we know that 4 is a node, right? And this node will be inserted into the tree. But we need to check the value of the node compared to our root node to know if this node is either going to be on this side or this side. Now we know 4 is less than 10. So that already tells us the node 4 is going to be the left child of the root node. Now, mind you, all values that are less than the root node goes to the left side, and all the values that are superior to the root node, the root node value will go on the right hand side. And the same thing will happen in the subtree, right? So when I insert a node in a tree, right, if this node does not have a value, or if this node does not have children, right, meaning it doesn't have a left or right child, then this node is known as the leaf node, right? So any node without child node is known as the leaf node. And if I set another value here, so let me just create a 5 here, this is also a sorry, 5 cannot be here, let's say this is 11. So this is also a leaf node, right? Until the node has a value, it remains a leaf node. But when it has a value, right, we then determine in which direction, or on which side we have to insert the new value that we are trying to insert in the tree. So let's say we have a next value called, let's put I'll say 12, right? Now 12 is superior to the root node, meaning 12 will go on the right side of the root node. But then there is another node here, there is an existing node, so we need to also determine if this 12, right, is going to go on the right side, or is going to be the right child of this node, in this case 11, or the left child. Now we know when there is a value superior to an existing node, that new node that we are trying to insert into the tree becomes the right child of our existing node. So in this case 12, right, 12 will become the right child of 11. So I'll put it here like this, will become the right child of 11. So let's do it this way. So we'll do it this way. So 12 becomes the right child of 11. And if we had, say, a 6, right? Now 6 is less than 10. So 6 will go on the left side of 10. But then 6 is superior to 4. So we do this. We put 6 as the right child of 4, right? So we'll do it this way and put it here. And the same thing will happen in this case. Let's say we have let's introduce one more node in the tree. So we'll create a node with the value 5. Okay, let's say value 3, right? I'm just trying to create a balanced tree here. So 3 is less than 10, so 3 is going to be the right, is going to be on the left of 10, which is the root node. And we also have existing nodes or subtree apart from the root node. So 4 would then check, right, if 3 is going to be the right child or the left child. Now we know 3 is less than 4, so 3 becomes the left child of the root node. So we'll put 3 here. So this is a basic overview of how a tree is constructed, right? How we insert nodes in a tree, how we determine the base of the tree, in other words, the roots. A tree has to have a root before we begin to insert other nodes in the tree. So we also learned about something called the height of the tree, right? So the height of the tree is basically the longest branch we have from the root towards or up to the last node in the tree. So in this case here, so we'll do the comparison for the left and the right subtree, right? So the longest subtree we have from the root will become the height of the tree, right? So here's what we have. So we have, from here we have 1, this is 1 length, and this is 2. And we'll also compare. So on the left, right, we have 2, and on the right we'll do the same thing, 1 and then 2. So this is also 2. So the height of this tree would have been the largest value we found, but in this case the left and right are equal, right? So this is right, they are equal, so the height of this tree, h, will be equal to 2. Now there is another thing we also need to note. which is the size of the tree. The size of the tree is the total amount of nodes we have in the tree. So we have 1, 2, 3, 4. Let me use a different color. 1, 2, 3, 4, 5, 6. So the size of our tree here, size is going to be equal to 6. We also learned something called the pre-order traversal, uh, which is a form of traversing a node or the nodes in a tree. So the pre-order traversal happens in a very um I'll call it an unusual way, but so the idea is to travel all the nodes on the left side of every subtree before traversing all the nodes on the right side of every subtree. So here is what it looks like. So the pre-order traversal would look like this. So first of all, we always start from the root node. So we'll go 10 and then we'll come here, right? We'll go 4. We come in this direction as well, which is also on the left. 3. Then before we come to the right hand side, which is 6. Then we'll go back before we now call every subtree on this right side, right? So we'll go here. This will be 11. Let's say we had 11 here, and imagine we had a node here, right? I'll just put an exclamation mark there. If there was a node here, we'll visit the left side of this node, which is 11 here, before we go to the right hand side, right? So our exclamation mark will be there, and we'll have another node, the last node, which is 12. So the reason why I'm using this exclamation mark here, you would have imagined maybe there should be a value here. I should have put maybe an 11 point something, right? Which is still less than 11 here. The reason why I did this is because in a tree, we can't have duplicate nodes. In other words, we can't have nodes with the same values, right? So a value less than 11 would have been 10, right? But 10 is already in the tree, which is the root node. So we can't have duplicates in the tree. So which is why I did this exclamation mark here. So that's pre-order traversal. Pre-order traversal basically visit all the left node, right? Or all the left all the nodes in the left subtree before visiting all the node in the right subtree for every node until the last node in the tree, right? So you can read about pre-order and post-order traversal. Oh, okay, we've not done post-order traversal. So I covered pre-order traversal, which is this. So as you can see, we use a recursive method to perform the pre-order traversal, which is upcoming. I think I made an implementation yesterday. Yes, so this is a pre-order traversal of every value in this node, right? In this tree, sorry. So I wrote a function for the insertion. So to insert nodes in a tree, you first of all check if the tree already has a root. If there is no root, then we insert the first value that we are trying to insert in the tree as the root of the tree. Then we begin to iterate through the left or the right based on the value of the node we are trying to insert on the tree. And if that value is less than the current value we have in the tree, in other words, if the new value we are trying to insert after we inserted a root is less than the root value, then we insert the new node as the left child of the root. Otherwise, we insert it as the right child of the root. So let me check the chat if there are any questions before we move on. Okay, so there are no questions at this point. So let's carry on. Now we have we have a few other stuff to discuss. It's so strange. I really feel tired today. I don't know why. Like my energy level is low. All right. Okay, so let's see what we have next. You know what? Let me walk you through the implementation of a tree in full. So we know a tree is made up of nodes, like that's the basic unit of a tree, right? A tree is made up of nodes. So we create a class for our node. So here's what we need to do. So say node. Ah, come on. Node. This is our node class. So we need to create a constructor function that will help us instantiate the node class. Now, when we create a node, we want to give it a value. So I'll put value here. And we'll need some properties for our node. So our node has a value, which is going to be the value that we pass in the instantiation phase. And we also have the right and left child. So I'll just put right is going to be none, and left is going to be none as well. All right. So the next thing we need to do is begin to implement the tree itself. So I'll call this class my tree like this. Hold on. And we need a few things for this tree. We'll first of all need to instantiate the tree without a value. And when we instantiate the tree, we need to set our root at that point, right? So we'll create the root property of this tree. So I'll create the instantiation method and say this, sorry, I'll set this dot self dot root is going to be equal to none at first. Now let's define our insertion method. I'll say insert node, right? So to insert a node, we will need to insert the node with a value. So I'll just put val there. And we'll need to, what else do we need? So we'll create a new node. I'll call this new node is going to be equal to node, and then we'll put in the value here. Now, we first of all need to check if our root has a value, right? Or if our root is a node. So say if self dot root is none, right? Then it means we need to, the new node we are trying to insert in the tree has to be our root node, right? Oh, come on. So we'll say, no, I don't like the spacing very much, but let me just leave it. So say root self dot root should be equal to our new node, right? So new node, and then we return. Now this return will only run this code if this condition is true. So anything else after this if condition here will not work, right? Now the next thing we need to do is, if there is a tree, if there is an existing node, in other words, if there is already a root node, we'll then need to decide where the new node we are trying to insert in the tree has to go. So let's say, so I'll call this current node. This will be my current node, and I'll set this to the root, self.root, right? Now the reason why I'm using current node is because this current node will will be the node we use to traverse the tree, right? So in every iteration, current node will either become the next node in the tree on the left side or on the right side. So this node will not remain, this current node will not remain the root. Instead, it will become something else, right? At some point. So this current node will help us traverse the tree, right? And we'll reassign it different values based on different conditions. So let's run a loop. So we'll say while true, right? Now this loop will run forever until we stop it. So now we need to check if the value we are trying to insert in the tree is less than our current node's value, right? So in the case where it is less, then it means it's going on the left side. Otherwise, it's going to the right side. So let's say if the value is less than the current node dot value, right, then it will go on the right side. Now, before we insert it on the right side, we also need to ensure that the right hand side, or sorry, it's going on the left side, right? We also need to ensure that the left side is the does not have any existing child. If he has a child, then we also need to set it as the left side of the sub child, right? So this is what I mean by that. Let me quickly show you. Imagine we had a tree like this. So there will be different levels of nesting. So here is my tree and this is 100, right? This is a root node. I have a value already. Now the new value I'm trying to insert, or the new node I'm trying to insert in the tree, is either going to be the left side or the right side. Now if the value of that node, of that new node, is less than the root node, then it means the new node will become the left child of the root node. Now the reason why it becomes the left child of the root node is, first of all, the root node did not have a left child, right? So meaning the left child for the root node initially was null, right? But in the case where there is already a child, let's say this is 20, right? And the value we want to insert into the tree is probably 18, right? Then we also need to check if this node here, which is after the root node, has a left child already. If it doesn't, then it is in that case we insert the value 18 into our tree, right? So let's do that. So we don't insert immediately. We also need to ensure that if the current node dot left, right, is none, right, then we set the current node dot left to be equal to our new node, and then we terminate the loop here, right? So we break here. Otherwise, right, else we set the current node to be equal to the current node dot left. So I'll put it like this. And we'll do the same thing for the right hand side, right? So this will be else if the value is superior to the current node value, then it's going on the right side, right? So we'll do this. We'll do the check again. If current node dot right, okay, hold on. I think I need to start using Vim. Just moving around these cursors is just, if current node right is none, right, then we set current node dot right to be equal to the new node. Otherwise, else, sorry, when we set it to the new node, we break. Let's be careful, otherwise we'll run into an infinite loop. Else we'll move on to the next right down the tree. So this will be current node dot right sorry, current node is equal to current node dot right. Oh, come on. All right, so here's all we need to do, and we can run some function to insert the nodes in the tree. Well, before we do that, we also need to look at the pre-order traversal, right? So I will properly see, how the nodes are inserted in the tree. So I will use this value here, right? So let's see. So let's create a function called the pre-order traversal. So this will be def pre-order traversal. This is a function, and this function will take a how many parameters? We need a node. Okay, let's put the root. I'll call this the root, and this will be the, I'll just call this results, because it's going to be the array in which we return all the nodes and in their respective order, right? Instead of putting root here, since I'm still in this class, I can use root directly. Or let me see, what did I do here? Okay, so I passed in the node. Okay, that's fair. So we need a node. Now this node will help us reassign or traverse the tree, right? So again, in each case we'll reassign a new value to this node, right? So for easier identification, I can just type this to be an instance of a node, right? Yeah, so that works. So here's what we need to do. We will first of all say if there is a node currently, right? Now we have to, traverse the tree recursively. First of all, we'll do pre-order traversal. So we'll call the pre-order traversal function. You know what? There is no need to define it in the class if we are going to use it outside of the class. So I'll bring it out like this. Okay, so we'll say pre-order traversal. Let's remove this cell from here, we do not need it. And pre-order traversal will do node dot left, right? And the result is basically a list. So this is going to contain all the values we need. So we'll append the values. So say result dot append. So let me add the list. So this is going to be a list like this. So let's import this list here. Yep. So result dot append, right? The node dot value. Okay, and we call this for, so we call this again, so we recursively call this function. We'll pass in the result again, and So we do this here. We'll call it for the right subtree as well. So node.right. So we travel the left subtree first before we travel the right subtree. So right node.right. Yeah. And then we pass in the result here again, which is a function, which is a list. And then I'll return the result at the end of the day. So return if I'm returning result, that means I'll have to, you know what, let's print the node here. Instead of doing this, I'll just print the node's value. So I can remove this part. I want the function to be outside so we can see how it works internally. So let's remove this part, right? And then we just print the node value. So print node dot value. Okay, so when we create an instance of our tree and we set value to the tree, we can call this preorder function, right, and pass it the root of our newly created tree, and it will automatically print out the value for us. So I'll call this values, or I'll call this values and set this to be equal to an array of values. So I'll put 10 to 19. Okay, let's put 11, 12, and 4, 5. Okay, so this is enough. You know, let's add one more bit larger values, which is going to be 15. Okay, so we do this. So we say for value in values, right? Let's first of all instantiate our tree. I'll say my tree is going to be equal to my tree class here, and we begin to insert values in this. So say my tree dot insert node value, right? So this will automatically create a new node for us. Once we pass it the value, which is this place, it will insert root as the head, it will insert the first node as the root node, and then subsequent ones will be inserted when this function is called. So we do this. So this prints. So let's print the tree. Let's traverse each node in the tree. Currently, if we run this function, right, nothing will happen because so there's an error here. Attribute of val. Where did I do val? Node has no attribute val. Value, I did value here, right? Oh, okay, so this current node of value. And where's the other one? Okay, so you can see nothing is printed yet because we are not returning anything. So let's call this preorder traversal function, right, and traverse the tree. So we'll say preorder traversal, and then let's print everything in the tree. So we'll call this, we'll pass it our roots. So we'll say my tree dot roots. Okay, so let's run this, and you can see we have 10 first of all, followed by 2, and you can see 4 is here because 4 is less than 10, so 4 is inserted on the left hand side. And then we go to 5. 5 will be the right child of 4, right? So we visit every left subtree before we visit the right subtrees, right? So see, you can see all of this here. This is printed before 15. Well, 15 was inserted after, so this is still going to be the left child of 23, right? Now we have 11 first of all. So 15 is not a direct, hold on. Yes, 15 is not a direct child of 23. if we had a value less than 23, then that value will be printed first before 23, right? Or what am I saying? So let's see, we want to print all the left child before the right child. So 11 came first, and then the next value we had was 23. So 23 becomes the right child of 11, right? So 15 would have been the left child of 11. So meaning there is a mistake here. 15 would have been printed before 23. I don't know why it's inserted this way. Let's see what's going on. Here's my implementation from yesterday, and we had some values here, so I'll just use these values. I'll call these values. You know what, let's pack these parts and see what went wrong. Okay, we also have this curved values. All right, let's just do it this way. I'll take these parts, these values here, and insert them in the tree to see what happens. Okay, so let's print. Oh, we still have 15 here. Maybe let's visualize this and see. So we have our tree started from, hold on. So we have a tree like this. Our first node was 11, or was 10, sorry. So first node will be 10. We have the next value here. Sorry, let me check the chat to see if there is any question. Hey Gabriel, welcome to the stream. Nice to have you here. Said, you're welcome. Yes, the language is Python. Yes. Thanks to Ransom for answering it. Okay, so let's continue. There is no question. There is no question yet. So we have 10, right? Our values are, let me just bring the array here. I'll paste it here. So here's what we have. We have 10. Let me bring this down. So we have 10, 2, 11, and you know what, let's delete this. Let's use a different color. So we insert values based on their we compare them to the root node, right? So the root node will be 10, and then the next node we have is either going to be a left node or a right node of this root node here. So the next value here is 2. 2 is less than 10, so 2 becomes the right node of the left node of 10. So this is going to be 2. And 11 is superior to 10, so 11 goes to this side. 11. Then we have 23. 23 is superior to 10, so 23 is superior to 10. 23 is superior to 11, so 23 becomes the right child of 11. So we do right child of 11. So we put 23 here, right? We visited 10, 2, 11, and 23. So the next value here is 4. So 4 is less than 10 but superior to 2, so it's the right child of 2, so we'll put 4 here. And 5 is also superior to 4, right? So 5 will be the right child of 4, so we'll put 5 here. Then 15 is superior to 10 superior to 11 but less than 23. Oh, I see why 15 was printed last. So 15 will be here. All right, that's good. So the traversal will happen in this form. So we visit 10, 10 will be first, then we decide. So we know the traversal is going to be every left subtree, right, before the right subtrees are visited. So we go from this point to this point here. We'll print 2, right? Let me properly write this out. So we'll have 10. Then from 10 we come to 2. From 2 we would have gone to the left side, but because there is nothing on the left, we move on with the right. So we'll go in this direction. So this will be 4. And from 4 we go to 5, right? And then we go back, right? We go back to this part, and then we start on the right hand side of this root node. So we'll have 11. Then we'll check if 11 has a left child, right? If 11 does not have a left child, then we'll carry on with the right child of 11. So 11 does not have a left child, we go on with the right child, which will be 23. And then from 23 we print 15 because 15 is the left child of 23. Hence our result, which is this here. So this is correct. This is correct in this case. So yeah, that's good. All right, so the next thing we need to do is solve a question. I'll solve one lead code question before we continue with the problem. Now, I'd already solved this question before the stream, just because I did not have anything to present for this stream today. So I quickly solved this question, and I will explain how I did it, and I'll provide the solution for us to practice with. So here's the question. Lead code number 700, search in a binary search tree. So you are given a root of a binary search tree, BTS, and an integer val. Find the node in the binary search tree that the node's value equals to val, right? Equals val. Okay. So find the node in the binary search tree that the node's value equals val and return the subtree rooted with that node. If such node does not exist, return null. So from our previous studies on trees, I think this question is quite straightforward, but if it isn't, we can actually go through the question again and try to understand what we are being asked. So let's come here. I'll take this image, I'll use this image as reference and try to explain with it, right? So let me remove everything from the screen now, and I'll take this file here. So here's an image of a tree we've been given as our input, and we want to return every value rooted with a particular value that we are looking for, right? Or in other words, every subtree rooted with our value. So our second input will be value, which is 2. So I'll write 2 here. So 2 is this. So we are looking for 2. So the question is asking us to find 2 in the tree, right? Find a node with a value that is equal to 2. In other words, our val here, right? The val input will vary based on the tree. So we are going to look for val, which is 2 here in our tree, and then once we find val, which is 2 here like this, we would then return the subtree, right, rooted with val, which means every child node of val will be returned along with it, right? So meaning if we found val here, right? If val was our current node, then we return this current node here. Now, when we return this current node, we know this current node has a connection with other nodes, right? If there were other nodes here, which, let's say this is 0 and this is 0.2, right? Oh, sorry, this is 1.4. I'm just using this as an example. Once we return this node, which is the current node, right, it will be returned along with every other node it is connected to. Now, because this node here is connected to this node, right? In other words, this node is the left child of this our target node. All its node will be returned alongside with this node once we return this node here. So let me show you what will happen in terms of code. So we will start with the root, right? The root is 4. Then we'll compare the value of this root to our value. Now the something interesting that will happen is once we compare the values, right, we'll know in which subtree we are searching for our value in, right? Because with the way binary search trees are structured, we know there is a left side which has less values than the root node, and we have the right side which has nodes with higher values than the root node. So since 2 is less than 4, it means our value, or this target 2, is possibly on the right side, on the left side of the root node. So we'll search down the left subtree of our root node. Now, when we arrive at this point, so let's imagine this was maybe 3, right? Let's imagine this was 3 and 2 was here. So we'll know, again, our search has to continue in this direction because 2 is less than our current node, right? But in this case, since the example gave us 2 immediately at this point, so there is no need for us to traverse down the tree. We know our value is 2, so we compare it with the value of this node, which is our current node here. And once we find this 2 here to be equal to this node's value, we simply return the node itself. Now, the node itself is connected to other nodes, so once we return it, it will return every subtree attached to it, right? So which is what the question is asking us to do. So first of all, they are trying to ask us to find a node with value equals to, with value, let me see, value same as our val inputs. I'll call this val inputs. And once that is found, right, so I'll say then, this is then return the node, right? So we'll return that node. Otherwise, else return null. Now, when do we return null, right? When do we return null? Now, when we search through this tree, imagine 2 was not here, right? Let's say we had 3 and maybe, you know what? Let's say we're searching for 0, right? Now 0 is still less than 4, right? So meaning we are traveling along the left subtree. So, and then when we get to this point, 0 is still less than 2, so we go to the left subtree. 0 is still less than 1, we still go down. But in this case, we no longer have anything, right? We no longer have any additional node. So our node ended here. Our tree ended at this point. Let me remove all of this. Oh, come on. our tree ended at this point, right? Our tree ended here, meaning we can't continue searching on the left side of this tree because this here will be none, right? So since there is no more left child in the tree for our value to be equal to, then we stop the iteration, right? There is no need for us to even assume, okay, the value will be on the right side, because the binary tree itself is structured in such a way that every value that is less than the current node will be on the left side, and every value superior to the current node will be on the right side. So if we don't find the current value along the a certain subtree, in the case where it is less than the root node, it will be on the right side. If we don't find it there, then we stop the iteration and we end we end the search there, right? So it means the node will never be in the tree if it's not on the left side. So here is the solution for that. We'll write the functions ourselves, right? So I've already provided the function here, but we can go ahead and do it again. So I'll create a file, which I haven't done. So this question is LeetCode 700 binary search. So I'll call this binary search value. So lit that's 700, which is going to be equal to binary the search value. So binary search BST. Okay, you know what, let's call this search BST. I'll rename this refactor. I'll say binary search tree, then search again, binary search tree search. So this is it. Let's copy this part of the code because we need it. You know, let's copy all of this from here to there, and we'll put this like this. Don't worry, we don't need this part. We don't need this either, right? But we need to uncomment this so that the tree is seen, the tree class is seen. So tree node, this is tree node, yes. Okay, the errors are gone. So we have one more error, but that's just a minor thing. So what we'll do here is we'll first of all create we'll get the root node, right? And then we'll traverse down the root node. So we'll say this will be our root node. I'll call this current node, like I called it before. Current node is going to be equal to the root, right? Now we need to traverse the root. So we'll say if while there is a current node, right? Now we need to compare the values. So if val is superior to the current node value, right, it means we are going to the right side. Otherwise we'll go on the left side if the value is less than the current node value. Now another thing to note is if the current node is equal to the current node's value is equal to our target value here, then we stop the iteration and return the current node. So we'll say if value is equal to current node dot value, right, then we end the loop here, right? So we just return current node. Otherwise there's another thing too. If the so while current node, right, so meaning if the current node value is none, the loop will end itself. So there is no need for us to write a condition to end the loop. So we'll then write the conditional statement to reset the current node, right? So value if val is less than the current node, right? If val is less than the current node dot value, meaning the val is possibly on the left side. So we'll just do current node will be equal to current node dot left, right? Dot left. Otherwise, else it's going to be superior to the current node value. So we'll say current node is going to be current node dot right. Current node dot right. So, and once we are iterating through, once this iteration is running, these conditions will be checked. So if it happens that we find a value in a node that is equal to our target value, the loop would be terminated here, right? Otherwise, we'll keep going until the current node is none, right? So meaning we probably set a left child to the node, and that node does not have a left child, obviously. So this will be none. Otherwise, we have to return something ourselves. So if nothing is returned and the loop is terminated, then we just return none, right? So this is all we need to do to solve this question. And I'll run this again. It's the same thing, right? So you can see I said if the current value of the current node value is equal to our value, we return the current node. Otherwise, we reset the node when the value is less than when the current node value is less than the value, then it means we are looking on the right subtree. So we'll reset the current node value to the right node. Otherwise, we do on the left node. And yeah, so if we don't find a value equal to the current node in our tree, if we don't find a value in our tree which is equal to our target node, then we return none. So let's run this function here. You can see, right? So I'll submit this again, which I already did. I don't know why I'm submitting it again. Well, anyways, you can see it's a very optimal solution. It works just fine, right? So that's my first 3 questions solved on LeetCode, which is quite okay, right? Now there's something you need to also let me come here. Now you can see my last submission now is still the same code, right? It's 93.3%, which means it's really good. But if you look at the same submission that I made previously, I'll go to my submission, right? And now I go, it's 45. It's still the same code. So I would say you shouldn't be too hard on yourself for this when it comes to these rankings, because I'm not sure how it is done, but it is not always accurate. So I will push this code to GitHub for you guys to have access to it. So I'll say git add git commit -m. This will be trees LeetCode trees like this, and -1 700. Yeah, it's 700. Git commit. Git push origin main. Git push origin main. Alright, so the code is now available on GitHub, and you can review it, you can use it to learn as well. Alright, What else do we need? Let me check the chat if there are any questions. Code. Okay, almost. Yeah. Code said, "Are you working?" I don't understand the question, but I was recording. Yeah. Okay, so there is another question from Ransom. Ransom is asking, no, don't know. Hell no. I've not solved 700 questions yet. So the thing is, Leeds Code numbers their questions, right? But I'm solving based on what I know. So this question I can solve it. You can see there are some questions I've solved previously that had even higher numbers, right? So it doesn't mean, let me see this question for example. It doesn't mean I've solved that much questions, right? So it's simply a numbering of the questions. So this is 27. I'm looking for a higher value. So let me say I go to stacks. Let's find out about stacks. And there is a question. So the numbering is not really how much question you've solved so far. Now you can see this question here. Remove the outermost parentheses, which I had solved before. So this question is number 1021. So obviously I've not solved 1000 questions yet. Yeah. I've not Code Wars, right? Yeah, I have a Code Wars account. I think Code Wars is cool, but I've not been active on Code Wars these days. So let's see Code Wars. I have a Code Wars account, right? Is it Code is Are you saying Codeware or Code Wars? I know about Code Wars, but I don't know about Code Wars. You can see Codeware is not anything related to data structures and algorithm. But if you look at Code Wars, there are problems here that are really really nice to solve. Um, so let me log in. I have a Code Wars account, so I'll log in into my account. Yeah, I think I need to start solving questions on Code Wars as well. I used to solve questions here, but anyways, it used to be nice. These were the days where I was just learning how to code. It was a long time since I solved a question, but I'll come back to Code Wars and try out some questions on Code Wars as well. Um, oh, you didn't know about Code Wars? Wow. Anyways, I've introduced you to Code Wars. You can find very interesting questions here to solve, right? So just have a look and play around with Code Wars. It's a really good platform. It's a really good platform. There is also HackerRank. HackerRank is also good. You can check HackerRank as well to solve questions on HackerRank. Anyways, this stream has come to an end, and thank you guys for being here today. If you have any more questions, you can you can send you can join the Discord channel. I created a Discord channel for us to interact more. Please check out the Discord server. Sorry, Discord server, and let's talk more. Let's solve more questions. I will really appreciate if Code Life joins the Discord server, because I think it seems to me you're saying you solved 906 lead code questions. That would be very, 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 very interesting. And I would like to, have more discussions with you outside um the stream. So again, the Discord server link is in the. I think I didn't link it in the description today. Let me see. I have it on my profile. So um I'll put it here so that you can also let me see, edit. Do I have it here? Yes. So the Discord server is here. Please kindly join and let me know. Let me know if uh let's connect. Oh my god, what happened? Okay, so I think I miscopied something. Oh, I copied the entire thing. Sorry. Let me put this here. Ransom is already in the Discord server, so yeah. Okay, so this is the Discord server. I would like to connect with you, Code Lifey, and you can join the Discord server as well. There are a few people there currently, Ransom and other people, so that would be nice. Yes, I am working. I think I'm beginning to get your question. Uh, yes, I work as a full stack developer. So if that's is your question, yeah. Anyways, thank you guys for coming through today. I'll see you guys tomorrow. And yeah, so join the Discord channel, the Discord server. I keep saying channel. Okay, join the Discord server and let's connect. It's not. Oh, I'm from Nigeria. Is it difficult to work where? Um, I it's just a startup, and I'm currently helping. So it's I'm working for I'm helping someone build a startup. Let's put it that way. So I'm currently the full stack developer. I build with I work with JavaScript and React and React Native. Yes. Okay. Bye. So how about you? Okay, you introduce yourself on the Discord server. I'm leaving now, so we'll talk more on the Discord server. All right. Okay. Bye. So let's talk more on the Discord server, guys.